So we do the same thing for the second layer. So we create a second weight matrix representing the nodes in between the first hidden layer and the next hidden layer. So as you can see here, these edges will be stored in that matrix. So far so good, right? And then at the very end, we do have another one called W3, which will be the weights in between the second layer and the output node, which is generally 1 or 2 or 3 nodes, and that will be your output. I'll explain the output layer in a little bit, but this is generally how a neural network would look like. And this is how we would set up all the matrices and the prerequisite knowledge that we need to start going into the math. So is there any questions so far? Great, cool. Okay, so let's take a look at this layer right here. So how do we normally process the information? So once we feed in the inputs, x, what happens to it? Like, it randomly changes into an output? Well, not necessarily, but I'll show you step by step what happens to x and what it turns into. So over here, if we feed an x into these 3 nodes, what it does is that it takes x, and this w, and then it does a linear combination of it. So x times w, and then it adds a bias term called b1. So if you guys remember, I think back in grade 9, back when you guys learned mx plus b, it's exactly the same thing. So x times w plus b will give you some sort of straight line. Great. Yes?
So then the inputs x have to be numerical?
They can be categorical as well, but we're assuming right now it is numerical.
Okay.
Yeah. For categorical, it can be a little bit, it's a little bit more complicated because we have to represent them in a different way. But let's just assume that everything is numerical. Okay, great. So now this is our equation, x times w1 plus b1. So the w1 is this weight, and the b1 is this bias term. And then we apply a nonlinear function to it called g of 1. And this nonlinear function will be the difference in between a neural network and linear classification. Okay, so now we apply this. Yes, yes. Yeah, that's a good question. Yeah, so actually sometimes, most of the time it goes from x1, x2, x3, and then a bias term at the very top. But then in this case, I just decided to flip it. I think it's generally because I wanted to put the bias at the very top to show you guys that it's not in the same, I guess, category as these like x1 values or like L1 values. Yeah, so it's generally the same thing. If you want to flip it, it should be still fully connected. Yeah. Is there any other questions? Yes.
Yeah, what nonlinear function is it?
I will be talking about it in a second. Great. Okay, so this is the second layer. We do the exact same thing as we did before. So we take all the outputs that we get from this layer onward, and then we multiply it with our weights, w, add our bias term, and then apply a nonlinear function. So if I were to represent it with an equation, it would be like this. So this g1 here would be from the previous layers. And that w2 would be from these edges right here. And then add the bias term, and then apply the nonlinear function. Yeah, so we're almost to the part where it goes like why are we applying this nonlinear function? Like, this doesn't really make sense. That's a good question. It's really hard to explain it to you guys because nobody really knows. But I will be talking about the functions in a little bit. Okay, so this is how our neural network looks. Pretty cool, eh? I hope that you guys now have a stronger understanding of how a neural network should look like. So at the very last node, the output, it also applies a nonlinear function, but this time there's no bias to it. So if we put that into an equation, it looks like this. So this G2 to this term was basically the output of this area. And then once you feed the output of this area into the output layer, the equation would look like this. And there's not supposed to be a B3 there, actually. Sorry, yes?
Oh, is there a reason why we don't add a bias at the last layer?
Yeah, that's a good question. I think generally because the bias in the last layer, I think, might not be learnable. I'm not 100% sure, actually. Yes?
I guess there's like lots of ways to set up these architectures as well.
Exactly.
So you can have biases in some layers but not others.
Exactly, yeah. So the reason why we actually want biases is because we don't want our neural network to always be, I guess, passing through the origin. So imagine if we have mx plus b, and we don't have the b term. Like, let's say if we just have mx. mx will always pass through 0, right? And in order to actually model a function that can simulate any other function in real life, or like model a function that can like learn the data properly, it doesn't necessarily have to pass through 0. So that's why we add the bias term. Great. So this is our neural network. Is there any questions? Yes.
So how do we have the weights, like
Yeah.
third weight function, if we don't include that in our function, like third weight matrix?
Yeah. So we have the third weight matrix. Yeah, so this actually has a small error in it. So this weight, yeah, so this weight matrix is supposed to be, there's supposed to be another weight matrix here, and there's not supposed to be a bias term over here. I did actually make a small error on that regard. But yeah, I think you guys can. Yeah, I'll post in a updated version soon. But yeah, yeah. So that's how it looks like. Is there any other questions? No? Cool. Awesome. So now I guess I'll talk a little bit about the activation functions, and maybe this will all fall into place for you guys. Okay, so the first activation function we have is called Sigmoid. So what is Sigmoid? Sigmoid is a function that kind of looks like this. What it does is that it takes any real value, like any real number, and it maps it to the interval 0 to 1. Non-inclusive. So it will never give you a value 1, and it will never give you a value 0. But it will go arbitrarily close. And why do we want this? That's a good question. So one problem that we really work on in machine learning is classification. And classification tries to predict a label, like yes and no, from on a question. So, for example, if we have the question, did this person survive or not, we can apply a sigmoid function as an activation function on a number. And this number will give us 1 or 0, which would mean yes or no. So this is the sigmoid function. It has vanishing gradients. What does that mean? I'll try to explain it. So what it does is that a vanishing gradient is a gradient that will continuously go to 0. So in this case, since the derivative of a sigmoid is always less than 1, if you keep applying activation functions, then the derivative of that chain of activation functions will slowly turn into 0. Because because the derivative of the sigmoid is less than 1. I hope that makes sense to you guys. Yeah.
Could you go
Cool.
over that?
Yep. So because we're applying activation functions in a chain, and if we want to apply a sigmoid for our activation function, and since it's in a chain, because the derivative of a sigmoid is less than 1, if you multiply numbers that are less than 1, if you multiply many numbers that are less than 1, it'll slowly go to 0.
Yes.
So we have a vanishing gradient problem with the sigmoid. So yeah, actually the gradient goes to 0 when x is very, very large. So if you take a look at that, at the graph over there, if x is very large, negative or positive, then the gradient will be very, very small. Cool. Now we have tan-h. Tan-h is very similar to sigmoid. It looks very similar too. So basically what it does is it takes any real value and maps it to -1 and 1. Also has the vanishing gradients problem. Yeah, so you guys might be wondering, hey, this looks kind of similar to sigmoid. And yes, it does, actually. So if you take a look over here, tan-h is a function of sigmoid. So that's actually pretty cool. Yeah, so we can use tan-h if we want to make an output of 1 or -1. So that's why tan-h is important. Okay, so now we have rectified linear unit. I will call it ReLU from now on, or R-E-L-U, I don't know. And basically what it is it's the maximum of 0 and x. So what it does is it takes a real value, a real number, and spits out either 0 or that number, if that number is positive, right? So that's pretty cool. So it kind of looks like this, where everything positive follows y equals x line, and everything negative is 0. So here's the question. What's the derivative at x equals to 0? Does anyone know? Yes, it does not exist. So if you guys learn from calculus, you can't really derive at that point. It's not smooth with like a lot of theorems. But the point that I'm trying to make is that the derivative is either 0 or 1. And because it's either 0 or 1, there's no vanishing gradient problem. However, there is such thing as an exploding gradient problem, and it does not quite mitigate that. Okay, so now I'm going to talk about the loss functions. So I'm only going to introduce one loss function to you guys, but just to let you guys know, there's going to be a lot more loss functions out there, and it's changing quite rapidly. But here's a very popular one that maybe many of you might know. So this one's called the mean squared error. Like maybe if you guys taken stats, you guys have probably seen this before. So basically what it is, I'll give you the intuition. It's if you have a neural network and it makes a guess. Let's call this guess yi. And if you have a label for the example, and that label is the ground truth. So that label is what happens in real life. We will call that yi squiggly. So the mean squared error is the difference in between our prediction and the ground truth. That all squared, and if we sum it up, then that would be the least squares, or our total error, and we divide it by n, which would be the average error that we make. So this is why it's called the mean squared error. So in a nutshell, it's basically a measure of how badly our network did. Maybe it did really bad, maybe it did okay. We're not entirely sure, but we can use this equation. And this may also have exploding gradients and has many shallow valleys. What do I mean by that? what I mean by shallow valleys is that when you actually look at the error function and you try to interpret it, it looks like a bunch of hills, and those hills have very shallow valleys, which is not good at all. So over here it says it's really not the best choice, but we will stick with this for now because we're learning and we're starting out. I think the mean squared error is actually a very good function for us to use for interpretability. So is there any questions? Yes.
Is n the number of passes through the network?
N is the number of examples that we have.
Okay.
Yeah. Any other? Yes.
Is it related to the variance at all?
Yeah. I'll just say yes. You can talk to me afterwards, and then we can talk about it. Yeah. Any other questions? So I guess like another point on the variance. So for neural networks, we don't really predict variance. That part's really hard. What neural networks does is like a point prediction, which is actually pretty cool. But if somebody can get like a variance prediction working, I think that would be like the next breakthrough. But I haven't seen that done so far. Yeah, cool. So now something about the loss is that we don't really want a high loss, right? So we want to minimize this loss. So one thing that we can do is basically use basic calculus. We can find the first derivative, I believe set it to 0, and then maybe find like a minimum, and then maybe alter our predictions to optimize for that minimum. That's cool. We definitely have thought of that, and turns out it's really, really, really slow. Like if you actually have an opportunity to find the first derivative without having too much of an impact on the runtime of the neural network, that's great. But since the neural network takes a very long time to run, which is actually very infamous of the network, we want to find a better solution than taking the first derivative. So what we created was gradient descent. And what does it do? So what we do is instead of taking the derivative, the whole derivative, we would take a partial with respect to the weights that we have defined. So what we would do is we would get the partial derivative, which would be the derivative at any point. So imagine if this is the loss function, and we take a partial derivative, we would get the values for this point right here. And since we know where the gradient is, for example, the gradient in this picture would be sloping this way, right? Then we know which the direction to follow for our next step. So what we would do is then take one step towards the gradient. So over here, we would take a step as large as alpha towards the gradient into our weights. And then we would update the weight that way. Okay. So we're trying to minimize the loss function by taking these steps to the minimum. Okay, so over here I mentioned why can't we use calculus? Backpropagation is much more faster. So in neural networks, we call this backpropagation. Okay, so here's a graphic of us taking steps towards the local minimum. Yeah, so this is defined by our alpha. Alpha controls how big of steps that we take. I'm not going to talk about regularization too much. It's pretty advanced. Well, no, it's not too advanced, but it's not good to have so much in mind when you're first learning this topic. So for regularization, just know that it helps with overfitting. If you guys don't know what overfitting is, don't worry about it. It's really cool. So like overfitting is like when you make a prediction, but then it's too in tune with what you've seen in the past. So like for example, if you have an exam and you study on the mock exams, but you only memorize what you see and you don't really understand it, and then come on the exam time, you only know how to answer the ones that you have practiced for. So you don't really know how to, I guess, you don't have a general understanding of the knowledge that you studied, and that's called overfitting. To help with this, we have techniques like dropout, early stopping, etc., etc. You guys can look it up on your own time. It's pretty cool. Okay, so let's tie all this together. So first things first. So imagine if we had a data set. Let I be the ith example of our data set, right? And we want to make a prediction on this example, right? So like, what's an example? An example would be like one entry that is like let's say name, sex, and age. Like let's say Bob, male, and he's 70 years old. So that's one example. And we put Bob through the neural network, and it gives us a prediction. And let's say this prediction is called yi, and yi says 1, which means he survived. Great, that's great. So Bob survived. Now what do we do? Okay, so now we take the error in between the prediction and the true label. Okay, so now let's imagine that Bob, we actually know what happened to Bob. Bob did not survive, unfortunately. So what happened? So what happens to the network is that we take our prediction, which is 1, subtract it with the fact that Bob died, which is 0, right? So then this would be 1, and then we would do that for every single person that we're trying to train on. So we would do that with Bob, with Alice, with Larry, right? And then we would sum up all of these squared errors that we have, and then we would take the average of it. And that would be our mean squared error. So now we have an error, and what we want to do with this error is we want to optimize for it. We want to make it really small. So what we would do is we would take steps towards the minimum and apply back propagation to adjust our weights to find this minimum and to optimize our neural network. Yes?
So in this case, J is MSC.
Yes, yes. In this case, J is our loss function. It's J. J is this function right here. Cool. So finally, we would then use these weights to make predictions in real life and like apply it to real life systems. So that's pretty cool. So now we can create a predictor that predicts whether someone died or not on the Titanic, for example. Okay, so let's get coding. I hope this presentation wasn't too boring, because there wasn't too much coding and like not too much application in this. So I'm going to be running you through an example on TensorFlow that I guess shows an example of like how you can use a neural network to play a small game. Cool. Yeah, what's up?
Once again, to the clock. Or can you open the collaboratory link actually?
Which one? This one?
Yeah.
Yeah. So how many guys? How many of you guys can open up this link? So the first link up there. Yeah. Okay. So I'm assuming it's working.
Yeah.
Yeah.
But also make sure you should see on the page it says open in playground mode. You want to click that so then you can make your own edits and then save it locally to your own Google Drive if you have that.
Cool. Awesome. So it should look something like this. What's on the screen? It's a little bit hard to see. Actually, let me try zooming in for you.
It's use the
Okay, what's the
control scroll.
true? But I also want the text bigger too.
Okay, it's responsive.
Is this visible for you guys? Hey guys, how does this look? Are you guys able to see in the back? Good? Okay, great. Cool. Okay, I know that was really long, but Hopefully we can run through this really, really quickly. Okay, so so first off, I'm going to be teaching you guys how to do reinforcement learning. So what's so special about reinforcement learning? Reinforcement learning is like teaching a neural network how to think based off of reinforcement techniques. So imagine if the neural network is like a baby, like it's crawling around and it sees a flame, like it sees like a match, for example, and it's on fire. And the baby doesn't really know anything, and it takes a look at it and goes, oh wow, that's shiny. And then it puts its hand into it, and then it goes, ow, that hurts. So that's an example of reinforcement learning. It's performing an action on the environment and then receiving a signal and then learning from that signal. Like memorizing that the matchstick was on fire and it hurt, so you'll never do it ever again. So that's what we're going to try to train our network to do. Okay, so the specific technique that I'll be using is called QLearning. It's going to be very primitive, but then it's actually very useful. So this is the type of learning that Google used back in, I believe, the 1900s to play Atari games.
1900s?
I believe it was 1900s, or like two...
You mean like 1990s?
Right, sorry, 1990s. Or
I mean, it's
two, technically it's correct. Technically it's correct. Yes, something around that time. I think I was just born. But anyways, yeah, so what is it used for? It's used for playing games, right? It's used for time series analysis. So if you guys are interested in like hedge fund analysis, like anything fintech, where we have a time series problem, then reinforcement learning applications are actually very effective on those type of problems. And there's also robots. We use them for like manufacturing and stuff like that. AI is very important there too. And generally, for any partially observable environments, we can apply this algorithm to, or like any partially observable Markov decision process problem. Right? So how does it work? So I said all this fancy stuff, but I haven't really told you how it works. So for QLearning, QLearning is a specific type of reinforcement learning which has three things: input, output, and what it learns. The input is the environment. So if the baby, so if the baby were to look at the match, that is one input. If the baby feels pain, that is another input. Actually, no, that wouldn't be an input. But for an output would be an action. So, for example, the baby would put his hand into the fire. That's an action. And what would our neural network learn? It would learn the expected reward from performing the action. So maybe the baby would put his hand in the fire like 5 times just to make sure it hurts. But it hurt every single time. So maybe it's not a good idea. But let's say if the baby wants to drink from a cup with a lid on it. And since the baby cups sometimes are not transparent, sometimes there will be water coming from it, sometimes there will not be water coming from it, but the baby does not know. So it tries to drink from it, and it learns the expected outcome from trying to drink the water from the baby cup. Cool. All right, so first thing that we have to do in order to get this set up is install our libraries, right? So we have matplotlib, random, pandas, TensorFlow, NumPy, etc., etc. I think really you guys are mostly interested in TensorFlow, so I'm going to be using this one the most. The other ones are just a nice add-on that I chose to really help illustrate this notebook. So let's try running this first. So for you guys, what you guys can do is that you guys can click this little play button right here, and then it will run it will run the code for you guys. But I'm running this on my local, so it might be a bit different. Okay, cool. Next we have to install OpenAI's Gym on our computers, but in your case, you're installing it on Collab, which is the Google Drive servers. So don't worry about installing anything on your computer. This will all be done on their servers. So if you run this as well, this is just to get the menu installed.
Why don't you just do it on Collab?
Because my thing's nicer.
Okay.
It's faster too.
Sure.
Yeah. Okay, cool. Okay. Now we need to import the environment. So over here, we have environment equals gym.make. We're trying to create a new environment for the carpool problem that we're trying to solve. So what is the carpool problem? That's a good question. So the carpool problem is, let's say if we have a cart and we can only go two directions, left and right, and if I put a stick on your cart and say that this stick cannot fall past 30 degrees, left or right, and you have to keep it balanced by going left and right, how can you solve it? It's very difficult for a person to do. I can technically make a simulation for you guys, but then I'm going to fail in like maybe 1 second. So we're going to try to get a computer to learn this. Actually, I'll give you guys a really quick, brief preview of how this will look like in a bit. Okay, so first things first. We have to run this, which imports our carpool environment. And then next, we want to take a look at what our environment does. So let's run the code after that. So over here, I will be taking 5 random steps in our environment. So we have our carpool problem, and what I wanted to test out is like, if I take random steps, what would happen? Like if I chose left and right randomly, like how will my cart perform? And if we take a look over here, we get some feedback from this environment, and we can use that feedback for the neural network. So over here, it says that we took action 0. I believe action 0 is left. I'm not 100% sure, but I can probably confirm and let you guys know later. But then once we take left on the environment randomly, we get back in observation. 4 values. I believe these values would be, I believe, your x coordinates and the angles of the cart, and something else. But it doesn't really matter because your neural network will learn it. Okay, and this is the reward that we're obtaining from taking that one step. So this game gives you a reward depending on how long you stay alive. So if you can balance the carpool for, like, let's say 30 frames, then it will give you a reward of 30, or I guess technically 29 steps. So here we have taken 5 random steps, and we got 5 random observations. Great. Okay, so now we can run this next piece of code. And what does this mean? So this basically means, how does our action space look like? So like, what kind of steps can we take? It turns out that we can only take steps that are integers and that are either 0 or 1. Hence, it's a discrete number of 2. Next, we also print our observation space, which is highs and lows. Observation space means that what is the bounds of which the carpool can fall under, and the horizontal bound of your cart. So this is the max and min of the observation space. So it's really nice to take a note of, but it's not the neural network part yet. So now we're going to jump into creating the neural network.
Can I ask a question?
Yes.
What did you say about the observation space? Was that the core vector?
Yeah. So
Are all these things?
yeah, good question. So The observation space is something that we get from the environment. So whenever we take an action on the environment, we get back an observation. So let's say if we have a cart and we have a pole on it, and let's say it's like arbitrary, but if we take a step right, if we move the cart right, maybe the pole will lean left, correct? So the observation space is the properties of the environment that you're observing. So these 4 parameters might just be, I believe it was the angles of the cart, no, the angles of the pole and the distance of the cart, the x coordinate of the cart, I believe.
So
Yeah.
the context of the charcoal,
Yeah.
you see one thing to tell you the angle, and one thing to tell you the
Yeah.
what's the whole thing?
Yeah, I'm actually not 100% sure. I have to look back at the docs, but if they're giving it us, yeah. We're going to be feeding this into the network anyways, but then it should say somewhere on the GitHub like what each and every observation is. Yeah. Yep. Yep. Yeah, that's a good question. Actually, I'll show you guys an example really, really quick. I think you guys might enjoy this. So what we're trying to solve is we're trying to create an agent that plays a game. And this game is to balance a cart pole without tipping the cart pole too far. So I'll show you guys an example right here. Okay, so if you guys can see this, it's a bit small, but like this is the neural network kind of trying to learn how to balance this cart pole. And I kind of, yeah, so if you can see, it's not doing very well right now because it's not learning very well. But I think at the end of this, like you guys might be able to create something that fully learns. Yep, so it's like slowly learning by itself, which is pretty cool. Yep, so the idea of the game is just to keep the pole balanced on the cart. That's cute. Okay, awesome. Great. Is there any other questions? Is there any other questions? Cool. Awesome. So now we have our observations, and now we know what kind of actions we can make on the observations. Let's see. Okay, so, yep, so we're right here. So let's create a input layer. And this input layer, I think we should make it size of 4 since we have 4 observations, right? And we also need an output size. I'm going to make that 2 because 2 will represent left or right. Usually we would use just one node for this, which would be 0 or 1. But in this case, I'm going to make it 2 because that's how we represent things in QLearning. Now we also have hidden layer. So I predefined the size of our hidden layer to be 15. So for every single layer in between the input layer and the output layer, there's going to be 15 nodes in every single hidden layer. Right? So we have an input layer and we have an output layer, and we have maybe 2 layers in between. And each hidden layer in between will have 15 nodes each, for a total of 30 nodes. Yes?
How did you decide on 15 nodes?
Arbitrarily. So you guys can test that with 15. You guys can test that with 10, 5. It turns out that, I don't know what's making this sound, but it turns out that the more nodes that you have, the more computationally expensive it's going to be, but sometimes it learns better, sometimes it just overfits. Yes?
How does it know that it's 2 hidden layers?
Yeah. I'm going to show you in a little bit how I'm going to create this neural network. Yeah. Cool. Awesome.
So
Yes.
it's about, I guess, building your network architecture so it
Yeah.
has a minimum, or suppress the number of nodes so it's less computationally expensive, but still gives you a good output so it trains fast.
Yes, exactly. And it really depends on the problem as well. So if the problem is really difficult, maybe you want to alter the architecture a little bit. Like maybe add more nodes, maybe add more layers, and maybe it'll perform better on the problem. Who knows? Yeah.
Is there like a general guideline on like what affects what? Because like
Yeah.
you can you can adjust the number of layers, but you can also adjust the number of nodes per layer, right?
Correct. Yep.
Like does adding more nodes do something different compared to adding more layers?
Definitely, definitely. I know, from what I know, adding more layers will give you a better guarantee that your function is more flexible and can fit other functions better. So I guess in this case, if you add more layers, your neural network will be able to learn more, and it will be able to generalize, I guess, a bit easier without getting too technical into it. If you add more nodes per layer, it will help a lot if the input, so like if your input is very, very large. So like let's say if you throw in a picture, for example, and this picture is like 1024 by 1024. That's a lot of inputs that like you have. And we need to kind of model this in a very high dimension. So we want to use a lot of nodes in like every single hidden layer to kind of encapsulate this high dimensionality. Yeah. So does that answer your question? Yeah. Is there any other questions? Cool. Great. So the next thing that we're going to do is going to reset this graph. So I guess you guys don't have to worry about this for now. It's like initialization, like to start it out. We just mandatorily like have it here. It's just nice to initialize our graph. Okay, so now we define the input layer. What are we going to have in the input layer? We're going to call it inputs, and we're going to make it the shape of 1 and input size. So it's going to be the shape of 1 and input size. And input size, I believe, is 4. So it's going to be a matrix of 1 by 4, which is basically what I've shown you in the slides before. Okay, so let's run this. Pretty cool. Great. Also, I believe it says like 1 by 2 there. I was actually trying to make this for a different example, but I haven't changed that to like 1 by 4 because the other example that I was planning for you guys just didn't work out. So, okay, cool. So now is the hidden layers. So how are we going to make the hidden layers? And I said that we're going to make 2 hidden layers, right? So how are we going to do that? Good question. So what we're going to do is we're going to call tf.getVariable. And what it does is that it creates those weights. And this weight matrix has to be of dimension 4 by 15, right? So if you remember back at the graph was like fully connected, right? There was 4 times 15 number of weights. So for every single input node, there would be 1 edge to the next layer, right? So for every single one, it would have 15 connections, and there's 4 input nodes. So therefore, it's 4 by 15. So over here, it would be input size by hidden size. So that would represent a matrix encapsulating all of our weights. Okay. And we will set the initializer to Xavier initializer. Really don't worry about that. Let's just say that it initializes randomly. So we set all these weight values to like a random number, but we choose it smartly. Yeah, but don't worry about that too much. Okay. And then we also have B1. B1 is our bias term. And for our bias term, we initialize it to 0. It doesn't quite matter too much. In this case, many people initialize it to a very small number, but 0 works pretty well. And yeah, cool. Yeah, so this is how it'll look like. So we created our first weights and our first bias. And what will we do to these weight and this bias? We will multiply the input times the first weight plus the bias term. So right here, what we will do is we will multiply tf.matmul, matmul as in matrix multiplication, the inputs, the weight, plus the first bias. And then we will apply a activation function on it. And in this case, I chose rectified linear. So tf.nn.relu. So this will be the output of the first combination. Yes?
Why are one of the lines like get variable and the other one's like variable when initializing like the weights versus the bias?
Yeah, Good question, good question. They're actually very similar. They're actually very similar. How can I explain this?
I do know, like,
Yeah.
because TensorFlow has like a representation of like the graph.
Yeah, correct. Yeah.
So like.
I guess for now, to not overcomplicate things, let's just imagine them as changeable variables, right? For now.
Okay.
Okay, great. Yeah, just take my word for it, guys. Okay, so we run these two, and now we work on the second layer. So how does the second layer look like? Right? So now we declare the second weights. That would be W2, B2, and layer 2, which is exactly the same thing. This time, for the second weight, it will be a matrix of 15 by 15. So that is the first hidden layer times the number of nodes in the second hidden layer. So that would represent all of the edges in between those two layers. So it's the exact same logic as the first weights that we had. Next, we will have B2, which is exactly the same as B1. And then we will do the exact same thing, multiply the first layer and W2 plus our bias term, and then add the activation function on top of it, which is rectified linear. So now it's starting to look like the equation that I built for you guys prior, that like f of g of 2 of g of 1 of like x times w plus like our bias terms, like that really long math equation is starting to look like that. Cool. So now we have our output layers. So it's pretty much the exact same thing. We have W3, we have layer out, no bias this time. And what we will do is multiply our second layer and the third weights together, and that will be our layer out, signifying that we will stop there and like produce an output. So layer out, in case this is not immediately obvious, it is actually very hard to see. Layer out will give you a matrix of, I believe, 2, because we have 2 output nodes. Right. And then now we will have to run this predict. What predict does is that it will call argmax on our layer out. And argmax would then take a look at the values in this matrix, which is a matrix of 2, and whichever one is larger, it'll return to either 0 or 1. Like, I guess if the 0th element is larger than the first one, then it will give you 0. If the second one is larger than the first one, then it will give you 1. So that would represent our actions, either 0 or 1. And like, whatever comes out of layer out should be the expected return we get from the environment. So if you remember the analogy that I made before, expected return is that if you keep trying to sample the environment many times, like let's say if you're a baby and you're trying to drink from your cup, but you don't know what's inside your cup, the expected return would be the expected amount of times that your cup has water in it, for example. So, and then the baby has to make a choice based off of what he knows, whether to drink from the cup or not drink from the cup. So over here is our prediction based off of what we know. Is there any questions? No? Cool. Awesome. All right, let me run all this first. Cool. Great. So now we have something called reward. This is just going to be a placeholder. So tf.placeholder, what that is just, that's hard to explain. It's just something that we can load values into while we are training our network. So what we're trying to do is we're trying to build the architecture of our network and then train it. So like what this placeholder does is just like put a little node somewhere randomly, and you can store values into it, kind of like a variable, but it doesn't change when you're training the network. So I call this reward queue, and what it does is it just holds a value. So now we have our loss, And what the loss does is that it will try to optimize based off of whatever we put into this variable and whatever we predicted. So over here, we call the mean squared error function. The MSE function that I taught you guys before, I believe it was like the 1 over m summation of like your guess subtracted by the true output all squared. And we would call that our loss function. So in this case, the reward Q is the true value, and our there out is our prediction value. So let's run this. It doesn't really do anything because we're still trying to set up our neural network. Okay, so don't worry guys, we're almost done. So now we need a trainer. So I picked the atom optimizer, and what it's supposed to do is it's supposed to simulate gradient descent, so it's like back propagation. This is all abstracted to you guys. Gradient descent is actually one of the harder topics to tackle in neural networks, but if you guys are really up for the challenge, please look it up. It's really cool. It's kind of like magic. I believe if you take Andrew Ng's ML course, he also says that it's magic. So if you don't believe me, you should believe him. Yeah, so here's Atom Optimizer. I selected a learning rate of 0.01, which is the alpha in the gradient descent. And I also created a variable called update model, which basically tries to, it uses this optimizer to minimize the loss. So we're making steps towards the local minima in the loss function by using this optimizer. So I hope that made sense. I hope that made sense to you guys. But like, please let me know if like any of you are confused at this step, because I believe this step is quite difficult to understand. No?
How do you choose your learning rate?
You guess. Yeah, so in papers, I believe the learning rate for the atom optimizer is by default 0.001. But then generally what machine learning people do is they try to fine tune the learning rate so that it learns perfectly on their problem. So it doesn't actually learn perfectly on every single problem. You might have to change this to like 0.05 if you're applying this algorithm to a new problem.
So we need like a neural net to optimize our neural nets.
Pardon me? Sorry.
We need a neural net to like help us pick our like.
Yeah. I actually have a friend doing that right now. I believe it's called Meadow Learning. It has something to do with like a technique called branch and bound. It's really cool. And if you guys want to work on that, that's going to be like the next new stuff, like automating automation. Awesome. Cool. Great. Okay. So now we have this initialization variable. So basically what it does is it initializes weights and biases. Generally, it would initialize it to random, and the biases would be really close to 0 or 0. Okay, now let's set it. So now let's try to train our network, and yeah. So this is the part that's going to be a little bit more hands-on, because we're now starting to pick the parameters that we want, and we want to use these parameters to train our network. So over here, I set a few variables. One is gamma. What is gamma? That is a discounted reward. Don't worry about it for now. Just take gamma as a variable. Next, we have a epsilon. One thing that I want to teach you guys about, like maybe a bit later, is called like epsilon greedy actions, like epsilon greedy searching. Take epsilon as a variable as well, and we also have like number of episodes. So that would also be exactly the same as number of examples, but this time it's episodes. So in reinforcement learning, we call multiple attempts episodes. So back to the baby example, if he puts his hand in the fire 5 times, that's considered as 5 episodes. So we want to do this 400 times, okay? And hopefully after 400 times, our neural network will be able to learn like what's good and what's bad. Okay, and then we also have declared our max steps. Max steps is the maximum number of steps before we completely shut it off. So in our example, we are trying to control a cart, and this cart can either go left and right. And because it can only go left and right, the reward is actually based off of how long it stays alive. So I put a cap on that, it's 500 for now. Great. Okay, so how do we use TensorFlow? Good question. So first thing that we have to do is define a session. So we have ses equals tf.session. It creates a new session on the graph that we have just created. And then in order to start it, we would call ses.runInit. If you guys don't remember, init initializes all the variables. So now we have our graph. Now the variables are initialized. Now what we want to do is that we want to run the graph and see what happens. So I'm going to try running the graph and show you guys like what's going to happen. Okay, so over here, if you guys can see, over here, we're going to try running one episode and see how the neural network does. What we do first is that we will create a new environment, and then as long as we are taking under 500 steps in this environment, we want to predict an action and then get the expected values of these actions. So these two will be the action and the expected value of the action. So like, how does these two get loaded from this command right here? So what session.run does is that it will run your neural network auto-magically, and it will give you two values. One of them is predict, and one of them is layer out. So predict and layer out are like variables that we have declared previously, right? So they're the variables that do the prediction. So we're going to automatically run TensorFlow to give us these two values. And these two values will be our action and our expected values, right? So for action, what we want to do is we also want to do a greedy epsilon greedy exploration. So basically what that means is that maybe our neural network is right, maybe our neural network is wrong, but at epsilon % of the time, epsilon is 5%. So 5% of the time, we're going to do a random action. So we're going to do a random action and see what happens. And like, why do we do this random action? That's because we want to do more like exploration than exploiting what we know, right? So if the neural network like maybe knows a trade secret and like keeps on like exploiting that trade secret, maybe we want to tell the network like maybe just like try something else to like experiment on it. Like 5% of the time, it won't hurt, right? So that's what we do. And then the next thing that we would do is we would apply this action onto the environment. And then we would get back a reward and an observation, and whether if we are finished or not. So our next observation, we would then run it through our network again in this line, and then we would get back another predicted expected value. So over here, it's exactly like the first session.run that we have performed right here. So we get back the layer out on the new environment that we have seen. And now from here on out, what we will do is that we will take that next environment and take that prediction that we made on the next environment and compare them and see if we made a nice guess or not. So I did some number crunching over here for you guys. I'm not quite going to explain it. If you guys want to read over it, please feel free, but it's just number crunching. It's a little bit hard for me to explain right now without going over the time limit. So I'm just going to skip this stuff. But basically what it does is that it just takes our two values and it just compares them together and like just adds some numbers. So over here at the very last session.run, we will want to update our model. And what does updating our model do? It will adjust it will calculate the loss function and it will adjust our weights based off of the loss function. Yeah, so basically everything that I've explained to you guys. So taking this and all the numbers that we crunched before, it will then optimize the model and try to lower the loss function. Okay? And then once we run this, we should get back a number. And this number will correspond how well it did in the first run. So let's take a look, actually. Oh, wow. It survived for 11 frames. Great. Usually monitors are like 30 frames per second. So 11 frames is like less than a second. So that's not quite very good. Okay, so I guess now what we can do is just train it for multiple episodes and see what it does. So over here, I basically copy and pasted all of the code from before. And what I did is that I made a loop for a number of episode times. So the number of episodes that we have defined was, I believe, 400. And we're going to just train it like 400 times and see what happens. So let's just run this. Oh, and one more thing. I believe on my notebook, I have this m.render thing uncommented because I'm doing it on my local. Since you guys are doing it on Collab, this stuff is commented out, so you guys can't really see the output, and that's because it's not on your local desktop. But then you guys can still run it and see the numbers that the neural network creates. So let's take a look at what this does. Let's see what happens when you do it 400 times. And this is the exact example that I was showing you guys from a few minutes ago. So basically, it's trying to learn how to navigate itself through the environment. And what it does is that it tries to print itself every 50 examples. I believe it's stuck, maybe it died, who knows. But then I believe you guys will see very soon. So I'm going to show you guys the numbers, and let's see what happened to the numbers. Okay, so over here, it displays every single episode and how it did on those episodes. So let's see if we can get anything over what we initially started with, which is 11 frames. Seems like it's not doing very well, actually. That's actually very unfortunate.
37.
Yeah. Actually, here there's a 47, so it survived for at least 1.5 seconds. So that's not too bad.
52.
Yeah, so there's a 52 here, and a 74 here. Hey, yeah, so it's there's a 243 here, so it's somewhat improving, correct? Yeah, so I guess after a while it does somewhat better, maybe, but I'm not 100% sure. I can't give you guys a good answer because this is just numbers, right? Yeah. Yeah, how about let's just plot this on a graph and see what happens. Wow, it looks pretty bad. Yeah, that's actually horrible. But why is it horrible? It's horrible because we're adding some sort of randomness to it. Maybe it's not learning because 5% of the time it's unlucky, right? And maybe it never actually learns that doing the right. So if I were to give you guys an analogy, if we had a baby and if we keep sticking its hand in the fire and it doesn't take its hand out, it will never learn that sticking its hand in the fire is a bad thing. So it'll generally adapt to that mindset. So this is a very extreme example, but I believe I'm able to get the point across. So it's the same thing as if you put a man in a cave for a few years, he'll start to adapt to the cave, and then if you open the entrance for him, he will never go outside because he's very suited to the cave. He does not want to leave. Okay, so what happens if we run this again? Maybe we're going to be a bit more lucky this time. Okay, so let's restart and clear output. Yeah, it should be okay. And let's try running this one more time, just for the sake of showing you guys. Okay, so like hopefully this will learn better, but I guess like as this training, is there any questions? Yes.
Can you go over like some of the terminology again? Because like there's your learning rate, and then there's like the epsilon, and there's all that.
Yeah. Okay. Yeah. Good question. So for some of the terminologies that I use that like might have been confusing to you guys, so I mentioned things like epsilon. Epsilon in this case is the percentage of chance that it will take a random step. So regardless of what it knows, maybe it'll just do something random. Epsilon number of times. So epsilon is a percent. In this case, it's 5, and it'll take a random action 5% of the time. Alpha is the learning rate, and the learning rate will be the step it'll take to try to minimize our loss function based off of the diagram that we had before. We also have other things like inputs, outputs, and hidden layers. Those are part of the neural network architecture. We also have gamma. Don't worry about gamma. It's part of the reinforcement learning process. So yeah. So let's actually take a look and see if it did any better actually. Yeah, it looks a little bit better.
Yeah,
Cool. Yeah, yeah. So like, there's a few 500 things here. So like maybe we got like super lucky, or maybe it just so happened to, I guess, learn super early, somewhat like a human can do. So let's take a good look at the graph. Yeah, so that's a lot better than like last time, right? I believe last time it was like kind of flat, and then there was like one spike, but now it kind of learned. And I believe if you try to run this on your own computer several times, you're gonna get like a separate, like a different graph than we're gonna get here. And that's like one cool thing about training these neural networks. Yes.
So like now that we've trained the agent, we can just like export it and then use it whenever we want. And
Exactly.
have the same level as the current one that we have.
Exactly. Yeah. So once you've trained it, you can export it, and then you can use it for pretty much any purpose that you like. So, well, I mean, we technically trained this agent to balance a cart pole, so it probably won't do anything. It probably won't do anything other than balance a cart pole. But if you train like a neural network that kind of like does something that you want it to do, and it's able to learn it, then you can export it and have it do whatever you would like it to do. So like that's actually one of the most cool and powerful things about the neural network. Yes. Yes.
So,
Yeah.
I didn't really understand why is it performing better the second time?
Yeah. Yeah. So the main reason why it's performing it's performing well the second time because maybe the first time it kind of got stuck somewhere and it didn't learn properly, I guess, how to get a good result. So, for example, if you have a person, and this person, I guess, yeah. So, if you have a person, and this person lives in a town, and this town serves very bad food, then this person will be eating bad food and doesn't really know how to like tell the difference in between good food and bad food. So for our agent, I guess we were just unlucky, and the agent kept seeing so the agent was not able to see a good outcome, so therefore the agent wasn't able to learn like what a good outcome looks like. So that's what happened to our agent. It was not able to learn because it was not able to actually like observe that kind of environment. So I really hope that makes sense to you guys, because it might look like magic. Yes.
So in some instances, it did extremely well. It got all 500.
Correct.
So
Yeah.
if you save the parameters where it did well and use them again, should you expect it to succeed? Like how much randomness is missing here?
Yeah. RAM really depends on the nodes itself. So the RAM scales on the nodes and the input data set. So the input isn't too large. It's like 4 nodes. Yeah. And I believe the weights the weights is like 15 by 15 times 2 plus something like that. Yeah.
So on this plot, there's some instances, say around 250 to 300,
right,
where it did well many times.
Right.
So take the weights of those times where it did well and use them.
And save them. Yes.
Should you expect it to do as well?
Right.
So within the simulation, is there a lot of randomness?
So in proper simulations, we would want to take out the random part. So imagine if you have a test, and if you answer questions randomly 5% of the time, that would not be good. I think you're gonna have like maybe expect 5% of the questions to be incorrect. So generally, when we test, we would take out the randomness. For this kind of graph, the reason why it did super well at around 300 and not so well at around like maybe 350 and 400, maybe the weights kind of diverged a little bit. Like maybe it's growing a little bit too big. Maybe we have something called like exploding gradient or like vanishing gradient, for example. There's many sorts of things that will affect the performance of a network. So this actually, I believe what's happening right here is that the expected values are, I believe they're diverging because we're using the rectified linear, and those explode. So I believe that's what's happening here, but I'm not 100% sure, and you're going to have to take a look at the parameters inside. Yeah.
And to add on to that, why don't we just stop once we reach 500 a certain amount of times?
Yeah. Yeah. That's a good question, and we absolutely can. Yeah. So generally what we would do here is that we would train the network and see where it performs best and do an early stopping, right? So then, like maybe it'll do really good, and then it'll perform a little bit bad, and then you kind of realize that like this dip right here, it's not really what we want. So let's just take the one right here and use that for production. Yes.
So you could be hitting like a local maximum.
Exactly, yeah. So you could be hitting a local maximum. So like what that means is, if we're trying to train a network and we try to find a minimum, but that minimum might not be the true minimum, right? There might be a minimum even smaller than that, like maybe somewhere far away, but we just haven't like got there yet. First thing that we have to do is like climb a few hills, and these hills increase our loss. And because these hills increase our loss, we're going to have a lower performance, such as this. So we're not 100% sure. We just have to train for longer. So is there any other questions? Cool. Awesome. Great. So over here, this shows you how to run the environment. It's pretty simple. We just take out the randomness to it, and we just so for production, we just set the actions as a prediction, and we would just apply it to the environment right here, and we would get back a bunch of variables. Yeah, it's very similar. It's very similar to training, but then we are just applying our predictions to it. Cool. So in our test, it actually performed 122 frames, which isn't too bad. It's a lot better than back when we first started, which was 11 frames, I believe. And then after once we're done, we do sets close on the environment. And here are like a few other like links to stuff if you're like really interested. If I kind of like persuaded you guys to learn more, please feel free to click these links. I mean, they're really good stuff. So I just want to leave you guys off with a little note before I close. So there's a few things that we need to keep in mind. So in neural networks, there's many different types of architectures. So depending on our problem, we want to use a different neural network to solve that problem. for example, computer vision uses convolutions. I believe NLP uses LSTMs, and there's like a lot more different types of architectures depending on your problem. We worked with a Q network which solves the problem of playing a game. So yeah, so definitely keep that in mind. Activation functions, hyperparameters, basically your whole network can be adjusted based off of like whatever you think is best. So you can like change the network however you want, and I guess change it depending on your problem. I guess you guys are the engineers, you guys make the network. Also, I'd like to say don't apply neural networks naively. Honestly, if you guys, like, I hear many people say, oh, neural networks, it's gonna solve all your problems. It does not solve all your problems. Sometimes, like, if the data is linear, just like draw like a line of best fit, and like that would solve the problem a lot more efficiently. Like, it's silly to think that a neural network will solve all of your problems, because more often than not, it generally doesn't. And one last thing is for data science, does neural networks fit into data science? I would say yes, but generally you don't need neural networks for data science. It's very nice to have in your toolkit, but you'll be very good with like many other tools like KNNs, SVNs, other ML kind of techniques that are out there in the field. And you really have to sanitize your data and visualize your data. Those are, I would say, as important as knowing how to make models. Yes?
So, like, what would the advantage of a neural network-based approach for something like a decision tree?
Yeah.
And what are the trade-offs?
Yeah. I believe random forests were really popular back in the days. They perform very well, actually. But then neural networks work, like, I believe neural networks have exceeded that in terms of things like high dimensionality and larger amounts of training data. With the expense of giving up, like, I guess training time, because it takes a long time to train these networks. And, well, I guess there's like a lot of trade-offs. I don't really want to mention them here, but like, I believe that it just performs better with a smaller amount of setbacks, if that answers your question. I guess we can always talk about it more, because, yeah, awesome. Yeah, and thanks so much, guys. Is there any, yes? Yep.
So what we used today was import the TensorFlow library instead of Python.
Yeah.
I know you can also use TensorFlow as the Google server, say.
Yeah.
What is the difference between using those two?
Yeah. There's actually no difference. Yeah. So what I ran for you guys was on my local, and that has the exact same setup as the one on the Google server. It's exactly the same. Yeah, I guess minus the GPUs. So for TensorFlow, they do have like standard versions, and you could change your version depending on which one you need. And I believe the Google servers has like the most recent, or like the second most recent version of TensorFlow. I believe you can always check. There's a command, I don't know it off the top of my head, but it will check the version of TensorFlow for you. But they should be exactly the same. Yeah. Is there any other questions? No? Yeah? Yes.
Is there any, so TensorFlow seems like pretty low level as far as like you're saying. What other high level libraries are there for neural network?
Yeah, there are definitely other high level libraries. I did actually want to teach you guys a library called Keras. It's like a build-on of TensorFlow. It basically abstracts TensorFlow to the point where you can make a neural network in like 4 lines. And the 4 lines are extremely simple and very easy to understand. There's other ones like PyTorch, but I believe that the next step should be, I believe that if you learn TensorFlow, it's a very valuable skill set. And I believe like a lot of, I guess, companies are starting to lean towards this kind of library. Is there any other questions? Cool. Thanks so much, guys. Great. I'm thirsty.